Welcome to Gate and Kernel. In the previous lessons, we started with logic gates. Then we used those gates to understand the half adder and the full adder. Now we are ready to move one level higher. A CPU does not just add individual bits. It needs to add numbers, subtract numbers, compare values, and perform logical operations such as AND, OR, and XOR. One of the main pieces of hardware responsible for those operations is the ALU. ALU stands for Arithmetic Logic Unit. It is one of the key execution components inside a processor. Chapter 1. What does an ALU do? At the simplest level, an ALU takes input data, performs an operation, and produces a result. We can call the two main inputs A and B. For example, A might contain the number 5, while B contains the number 3. But there is an immediate problem. Just knowing A and B is not enough. Should the ALU calculate A plus B? Should it calculate A minus B? Should it perform A and B? Or perhaps compare A and B? The ALU needs another input that tells it what operation to perform. We can call this ALU Control. So an ALU has two different kinds of information coming into it. The data inputs tell the ALU what values to work on. The control input tells the ALU what to do with those values. That distinction is fundamental. Data and control are not the same thing. The ALU combines them to produce the correct result. Chapter 2. Arithmetic and Logic. The name Arithmetic Logic Unit tells us that the ALU handles two major categories of operations. The first category is arithmetic. Typical arithmetic operations include addition and subtraction. The second category is logic. Typical logical operations include AND, OR, and XOR. Many ALUs also support comparisons or provide information that helps the CPU perform comparisons. So conceptually, we can imagine an ALU as a hardware block with several possible functions inside it. Add, sub, AND, OR, XOR, compare. The processor does not necessarily activate all of these operations as the final result at the same time. Instead, control logic selects the operation required by the current instruction. This is one of the reasons the ALU is so useful. The same general hardware path can support many different instructions. Chapter 3. Addition inside the ALU. We already know the basic building block of binary addition. A full adder takes three 1-bit inputs, A, O, B, and carry in. It produces two outputs, sum and carry out. But a real processor normally works with much larger values. For example, a 32-bit processor may operate on 32 bits at a time. A 64-bit processor may operate on 64 bits at a time. That means the addition hardware inside the processor must handle many bit positions together. We are not going to study the detailed multi-bit adder design in this lesson. For now, we will treat the internal adder as a hardware block. The important point is that the ALU contains real digital circuitry that performs binary addition. Suppose A is 5. In 4-bit binary, 5 is 0101. Suppose B is 3. 3 is 0011. The ALU adds them. 0101 plus 0011 produces 1000. That is 8. So 5 plus 3 equals 8. But notice what is really happening. The ALU is not running a little software program that says 5 plus 3 equals 8. Electrical signals representing zeros and ones enter digital circuits. Those circuits produce another pattern of zeros and ones. Arithmetic emerges directly from hardware. That is the important connection between the full adder we studied earlier and the arithmetic performed inside a CPU. Chapter 4. Subtraction inside the ALU. Subtraction is especially interesting because computers can reuse much of the same arithmetic idea used for addition. Suppose we want to calculate A minus B. Mathematically, we can rewrite that as A plus negative B. So instead of thinking of subtraction as a completely unrelated operation, we can think of it as addition with the negative version of the second operand. This is where 2's complement becomes extremely important. Consider the 4-bit number 3. 3 is 0011. To form -3 in 4-bit 2's complement, invert the bits. 0011 becomes 1100. Then add 1. 1100 plus 1 gives 1101. So 1101 represents -3 in 4-bit 2's complement. Now 7 minus 3 can be treated as 7 plus -3. In real processor hardware, a common design idea is to reuse the adder for both addition and subtraction. For subtraction, the B input can be complemented and an extra 1 can be introduced through the arithmetic path. Conceptually, this produces a plus the 2's complement of B. We do not need to build that circuit in detail yet. The important idea is much bigger. 2's complement allows addition and subtraction to share much of the same arithmetic hardware. That reduces duplication and makes the ALU much more elegant. Chapter 5. AND operation. The ALU also performs bitwise logical operations. Let us start with AND. For 1 bit, AND produces 1 only when both inputs are 1. 0 and 0 gives 0. 0 and 1 gives 0. 1 and 0 gives 0. 1 and 1 gives 1. Now suppose A is 1100. And B is 1010. The ALU performs AND independently at each bit position. The first pair is 1 and 1, which produces 1. The next pair is 1 and 0, which produces 0. The next pair is 0 and 1, which produces 0. And the last pair is 0 and 0, which produces 0. So the final result is 1000. This is called a bitwise operation because each pair of bits is processed independently. And is extremely useful for masking bits. For example, software and hardware can use a mask to keep certain bits while clearing others. Chapter 6. OR operation. OR is another bitwise logical operation. For 1 bit, OR produces 1 when at least one input is 1. 0 or 0 gives 0. 0 or 1 gives 1. 1 or 0 gives 1. 1 or 1 also gives 1. Again, let it be 1100. And B be 1010. The ALU applies OR 1 bit position at a time. The result is 1110. So 1100 or 1010 produces 1110. Like AND, OR is often used when software or hardware needs to manipulate selected bits inside a word. Chapter 7. XOR operation. XOR means exclusive OR. XOR produces 1 when the two input bits are different. If the bits are the same, XOR produces 0. 0 XOR 0 gives 0. 0 XOR 1 gives 1. 1 XOR 0 gives 1. 1 XOR 1 gives 0. Now let A be 1100. And let B be 1010. Performing XOR bit by bit gives 0110. We have already seen XOR before. In a half adder, the sum output is a XOR B. So this is another useful connection. The same basic logic operation that appeared in a tiny 1-bit arithmetic circuit also appears as a full-width operation inside the ALU. The scale changes. The underlying logic does not. Chapter 8. How does the ALU know what to do? This is one of the most important ideas in the entire lesson. Imagine the ALU receives the same two inputs every time. A is 0101. That is 5. B is 0011. That is 3. Now watch what happens when only the control signal changes. If the ALU control selects ADD, the result is 1000. That is 8. If the control selects N, the result is 0001. If the control selects OR, the result is 0111. If the control selects XOR, the result is 0110. The input data did not change. A is still 5. B is still 3. Only the selected operation changed. And because the operation changed, the result changed. This gives us a very useful way to think about the ALU. A and B answer the question, what data are we working on? ALU control answers a different question, what should we do with that data? Conceptually, we might say that control value 000 means AND. 001 means OR. 010 means ADD. 110 means SUB. And 111 means compare. But those exact codes are only examples. Different processor designs can use different encodings. The key idea is not the specific numbers. The key idea is that control signals select the ALU function. And where do those control signals come from? Ultimately, they come from the CPU's control logic after the processor determines what instruction it is executing. This is the bridge between an instruction and the hardware operation that actually happens. Chapter 9. Where do the ALU inputs come from? An ALU processes data, but it is not normally used as long-term storage. So where do A and B come from? Very often, they come from CPU registers. Registers hold values that the processor is actively using. One register can provide the first operand. Another register can provide the second operand. Those values travel through the processor's data path into the ALU. The ALU performs the selected operation. Then the result can move somewhere else. It may be written back into a register. It may be used as an address. It may contribute to a branch decision. The exact destination depends on the instruction. So registers and the ALU have very different jobs. Registers store values. The ALU transforms values. That difference is simple, but extremely important. Chapter 10. The ALU and the register file. Now we can connect this lesson directly to the register file. A register file is a collection of CPU registers with hardware that allows the processor to read and write them. In a design such as the MIPS register file we discussed earlier, there are 32 general registers. That means the hardware needs 5 bits to select one of 32 register locations. A typical register file also provides 2 read paths. Read port A can supply one operand. Read port B can supply another operand. This arrangement is extremely convenient for instructions that use 2 source registers. The 2 values leave the register file and enter the ALU. After the ALU produces a result, that result may travel back to the register file through the write-back path. So a simplified data path looks like this. Register file. 2 read ports. ALU. Result. Write back. Register file again. This is one of the basic patterns that appears again and again inside a processor. And there is another important lesson here. The register file does not perform the addition. It only provides the values. The ALU does the arithmetic. Afterward, the register file can store the result. Storage and computation are cooperating, but they are different hardware functions. Chapter 11. Example, ADD instruction. Let us follow a complete example. Consider the conceptual instruction, add R1, R2, R3. Its meaning is, R1 equals R2 plus R3. Suppose R2 contains 5. And R3 contains 3. First, the register file reads R2. The value is 5, or 0101 in our small 4-bit example. Second, the register file reads R3. The value is 3, or 0011. Those 2 values become the ALU inputs. At the same time, the processor's control logic tells the ALU to perform ADD. The ALU adds the 2 values and produces 1000. That is 8. Then the result travels through the write-back path. Finally, the processor writes 8 into R1. So the complete flow is read R2. Read R3. Send both values to the ALU. Select ADD. Produce the result. Write the result into R1. This is much closer to what actually happens inside a processor than simply saying, the CPU adds 2 numbers. We can now see where the numbers come from, where the operation happens, and where the result goes. Chapter 12. Example, an instruction. Now consider another instruction, and R1, R2, R3. The structure of the data path is almost unchanged. The register file still reads R2. The register file still reads R3. The 2 operands still travel to the ALU. The result can still be written back into R1. So what changed? The ALU control signal. For the previous instruction, the control logic selected ADD. For this instruction, it selects AND. That one change causes the ALU to interpret the same kind of input path differently. Instead of adding the operands, it performs bitwise AND. This is a powerful idea. A CPU does not need a completely separate data path for every instruction. Much of the same hardware can be reused. The register file can supply operands for many instructions. The ALU can perform many different operations. The control logic determines how those shared hardware blocks behave for the current instruction. This reuse is one of the fundamental ideas behind processor data paths. Chapter 13. Comparisons. Programs constantly make decisions. Is A equal to B? Is A smaller than B? Is A greater than B? An ALU can help answer these questions. The easiest case to understand is equality. Suppose A is 5 and B is 5. If the ALU calculates A minus B, the result is 0. 5 minus 5 equals 0. Therefore, if A minus B produces 0, A and B are equal. This is why a 0 indication can be useful for comparisons in branches. Less than and greater than comparisons require a little more care. Signed and unsigned numbers are not always compared in exactly the same way. A processor may use the arithmetic result together with sign, overflow, carry, or dedicated comparison logic, depending on the architecture and instruction. So we should not reduce every comparison to one simple flag. But the main idea remains clear. The ALU is not only a calculator. Its arithmetic results can also provide information that helps the CPU make decisions. That connects the ALU directly to conditional branches and program control flow. Chapter 14. ALU status outputs. The main output of the ALU is usually the result. But an ALU can also produce additional status information. Common examples include 0, carry, overflow, and negative. 0 indicates that the result is 0. For example, if A minus B produces 0, that may indicate that A and B are equal. Carry is associated with carryout from binary arithmetic and is especially useful when working with unsigned values or multi-word arithmetic. Overflow is different from carry. Overflow is concerned with whether a signed arithmetic result is outside the range that can be represented with the available number of bits. This distinction matters. Carry and overflow are not the same thing. For example, an unsigned calculation may produce a carry without representing a signed overflow. A signed calculation may overflow even when the carry behavior is not what a beginner expects. Negative usually reflects the sign of a signed result, commonly related to the most significant bit in 2's complement representation. Different processor architectures expose and use these status signals differently. Some architectures have a dedicated status register. Others use comparison instructions in different ways. So we do not need to memorize one universal flag system. The important lesson is this: the ALU can produce more than a number. It can also produce information about that number. And the CPU can use that information to control what happens next. Chapter 15. The ALU is not the entire CPU. The ALU is important, but it is only one part of the processor. A CPU also contains registers. A register file. Instruction decoding logic. Control logic. Caches. Internal buses. Multiplexers. And many other data path components. The instruction decoder helps determine what instruction the processor is dealing with. The control logic generates signals that configure the data path. The register file supplies operands. The ALU performs the selected operation. Other hardware determines where the result goes. Memory-related hardware may send data to or receive data from caches in memory. So the ALU does not decide everything by itself. It is an execution unit working inside a much larger coordinated system. A useful way to think about the CPU is not as one giant calculator, but as many specialized hardware blocks passing data and control signals between one another. Chapter 16. From logic gates to the ALU. Now we can connect the entire story. At the lowest level, digital circuits are built from transistors. Transistors can be arranged to create logic gates. Logic gates implement basic Boolean operations such as AND, OR, XOR, and NOT. Those logic gates can be combined into more useful circuits. An XOR gate and an AND gate can form a half adder. More logic can form a full adder. Full adders and related circuitry can be combined into wider arithmetic hardware. Arithmetic circuits and logical circuits can then become part of an ALU. The ALU connects to registers, control logic, and the rest of the processor data path. And those structures together become part of a complete CPU. So the progression looks like this: transistors, logic gates, Boolean operations, half adder, full adder, arithmetic circuits, ALU, CPU data path, CPU. This is one of the most important ideas in computer architecture. A modern processor may execute billions of instructions and contain an enormous number of transistors. But the underlying principles do not begin with something mysterious. They begin with very simple electrical switching. Step by step, simple circuits are combined into more powerful circuits. And eventually, those circuits become the hardware that executes software. Chapter 17. Conclusion. The ALU, or Arithmetic Logic Unit, is one of the key execution components inside the CPU. It performs operations such as ADD, SUB, AND, OR, XOR, and comparisons. The ALU usually receives operands from other parts of the processor, often from the register file. Those operands become inputs A and B. The ALU also receives control information that tells it which operation to perform. The same two input values can therefore produce completely different results depending on the control signal. After the operation, the ALU produces a result. It may also produce status information such as 0, carry, overflow, or negative. The result can then move through the CPU data path and may be written back into a register. So a simplified execution path looks like this. The register file provides the operands. The ALU performs the operation. The ALU produces the result. The result is written back. And the control logic coordinates the entire process. We started with logic gates. Then we built a half adder. Then a full adder. Now those ideas have brought us to the ALU. And for the first time, we can clearly see how simple digital logic becomes a real execution path inside the CPU. The next question is just as important. How does the processor examine an instruction and generate the control signals that tell the ALU, the registers, and the rest of the data path what to do? That takes us to instruction decoding and the CPU control unit. Thank you for watching Gate and Kernel. I will see you in the next lesson.